This video series delves into solar energy and photovoltaic panels, covering everything from the fundamentals of sunlight and solar energy to the science behind PV panels, the mathematical modeling of photovoltaic systems, simulations, and more. In this video, we kick off with an in-depth look at solar energy. Discover what solar energy is, details about solar light, and why it stands as one of the most promising renewable resources. We'll explore the benefits, challenges, and real-world applications of solar energy, showing why it's crucial in the fight against climate change. We all know that sunlight isn't available at all times, and this is because of the Earth's movements in space. As the Earth orbits the Sun along the ecliptic plane, the Sun's position in our sky appears to shift, causing seasonal variations in sunlight. Plus, the Earth is tilted on its axis at about 23.5 degrees, and as it rotates, this tilt changes how the Sun's light reaches us throughout the day and year. When we talk about capturing solar energy, understanding the Sun's position is crucial. To describe it, we use something called the azimuthal coordinate system, which includes two main angles. First, there's the azimuth angle, which shows us the Sun's direction relative to true north, from 0 degrees all the way around to 360 degrees, with 90 degrees representing east, 180 degrees south, and so on. Then there's the altitude, or elevation angle, which measures how high the Sun is above the horizon, from 0 degrees at sunrise and sunset up to 90 degrees when it's directly overhead. Tracking these angles helps us determine the Sun's exact position in the sky, allowing us to position solar panels in a way that maximizes energy capture. So when we talk about solar energy, the movement and position of the Sun are key factors that help us harness its power more effectively. When we talk about harnessing energy from the Sun, we're actually capturing energy from particles called photons. The Sun radiates or emits electromagnetic energy, sending out these energetic photons across space. In quantum physics, photons are known as wave particles, stable with an invariant mass of 0, always traveling at the speed of light through a vacuum. The energy of a single photon can be calculated by multiplying the photon frequency by Planck's constant. The electromagnetic spectrum, which spans from very short gamma rays to long radio waves, includes only a small range visible to the human eye, about 400 to 700 nanometers. Light with shorter wavelengths, like ultraviolet and X-rays, has higher energy, while infrared and radio waves have longer wavelengths and less energy. Photovoltaic technology is most interested in the ultraviolet, visible and infrared parts of the spectrum. Now let's see what happens when sunlight reaches the Earth's atmosphere. As sunlight travels through the atmosphere, several factors impact the solar radiation that reaches the surface. First, the solar radiation is reduced due to absorption, scattering, and reflection by gases, dust, and aerosols in the atmosphere. This means not all of the energy from the Sun makes it to the Earth's surface. Additionally, the composition of the atmosphere changes the spectral content of the solar radiation. Some wavelengths of light are absorbed more than others. For example, ozone absorbs ultraviolet light, while water vapor and carbon dioxide absorb far infrared light, creating dips in the solar spectrum. However, the overall power reduction is more significantly caused by scattering and absorption by air molecules and dust particles. For the study of photovoltaics, it's essential to understand the concept of air mass, or AM. Air mass describes the path length that sunlight takes through the Earth's atmosphere, normalized to the shortest possible path when the Sun is directly overhead. This measurement helps quantify the reduction in solar power as light passes through the atmosphere and is absorbed or scattered by air molecules, dust, and other particles. The scientific community has adopted a specific air mass value, AM equals 1.5, as a standard for solar measurements and calibrations. This standard, AM 1.5, corresponds to a solar elevation angle of about 41.8 degrees. By using this standard, researchers and engineers can create consistent benchmarks to evaluate and optimize solar panel performance under realistic conditions, making AM 1.5 crucial in both testing and predicting photovoltaic efficiency in everyday environments. In the final part of this video, let's discuss what happens when sunlight reaches the surface of a PV module. The power a PV module receives isn't just about sunlight intensity, it also depends on the angle at which sunlight hits the module. When the sunlight strikes the module at a perpendicular angle, the module captures the maximum possible power density. However, since the sun's position shifts throughout the day, the angle between the sunlight and a fixed module keeps changing. This constant variation means that a fixed PV module usually receives less power than the full sunlight intensity. Now let's calculate the radiation incident on a tilted surface. In the shown figure, the equation for S module and S horizontal is given by, where alpha is the elevation angle and beta is the tilt angle. For a module at an arbitrary tilt and orientation, the equation becomes a little more complicated, where alpha is the sun elevation angle, and theta is the sun azimuth angle, and psi is the azimuth angle that the module faces.